Welcome to the lesson on irrational numbers. At the end of this lesson, you will be able to define irrational numbers and represent irrational numbers on a number line. You must have guessed that these numbers are not rational numbers. Such numbers are called irrational numbers. To understand an irrational number, we'll recall the definition of rational numbers. Numbers that can be written in the form of p upon q, where p and q are both integers and q is not equal to 0, are called rational numbers. The collection of rational numbers is denoted with the letter q. Now, let's consider the numbers that are remaining. Can these numbers be expressed in the form of p upon q? No, none of these numbers can be written in the form of p upon q. Let's read out the formal definition of irrational numbers. Numbers which cannot be expressed in the form of p upon q, where p and q are integers and q is not equal to 0, are called irrational numbers. The collection of irrational numbers is denoted with q bar. Next, let's see where these numbers can be placed on the number line. We'll begin with the representation of square root 2 on the number line. The method that we are about to discuss was discovered by the Greeks. Let's see how they represented these numbers on the number line. Consider a right-angled triangle OAB. Its base OA and height AB is 1 unit each. Here we need to find the hypotenuse OB. Recall the Pythagoras theorem that states, in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Applying this theorem to triangle OAB, we get this equation. On substituting the values of OA and AB, we get OB square is equal to 2. Therefore, OB is equal to the square root of 2. If we represent OB on the number line, it means we are representing the value of the square root of 2. The vertex O of the triangle must coincide with the 0 on the number line. The vertex A will coincide with 1 on the number line. In order to represent the square root of 2 on the number line, mark the length OB with the help of a compass. Then, taking O as the center, we'll draw an arc on the horizontal line. Let's mark the point of intersection of the arc on the number line as C. The distance between O to C is the square root of 2. Hence, point C represents the square root of 2 on the number line. Similarly, we can represent square root of 3 on the number line. Let's see how. In the same figure, through C, draw CD perpendicular of 1 unit length. Join OD to get right-angled triangle OCD. Applying Pythagoras theorem for right-angled triangle OCD and substituting the values of OC and CD, we get OD squared as 3. Therefore, OD is equal to the square root of 3. With O as the center, mark the length of OD with a compass and draw an arc on the horizontal line. Wherever the arc intersects the horizontal line, mark that point as E, and the distance from O to E is the square root of 3. You can now proceed to the solved problems section to apply your learning.